General relativity, proposed by Albert Einstein in 1915, is one of the most important theories in all of modern physics. It completely transformed the way we understand gravity, space-time, and even the structure of the universe. Before Einstein, it was Isaac Newton who provided the explanation for gravity. According to him, gravity is an attractive force between two bodies with mass. The more massive the objects, the stronger this force is. And the further apart they are, the weaker it becomes. This theory explained with tremendous success the falling of objects on Earth, the motion of the Moon, and the orbits of the planets around the Sun. For more than 2 centuries, Newtonian mechanics therefore seemed sufficient. It was simple, effective, and very accurate in most situations. But over time, certain highly precise observations showed that this theory was not complete. One of the most famous problems concerned the planet Mercury. Mercury is the planet closest to the Sun, so it's the one most strongly affected by its gravitational influence. By observing its orbits very precisely, astronomers noticed an anomaly. Its perihelion, that's the point in its orbit where it is closest to the Sun, was gradually shifting over time. A large part of this shift could be explained by Newtonian theory because of the influence of the other planets. But there remained a small discrepancy that Newtonian mechanics could not account for. This detail might have seemed minor, but in science, a small anomaly can reveal a major flaw in a model. This was in fact one of the first great successes of general relativity. It made it possible to explain precisely the advent of Mercury's perihelion. Alright, that covers the origins. Let us now focus on the essential point. Einstein's central idea is the following. Gravity is not a force in the usual sense, but a consequence of the curvature of spacetime. In other words, the presence of matter and energy distorts the geometry of the universe, and objects then move through this curved spacetime. To visualize this, people often use the image of a heavy ball placed on a stretched sheet. The ball creates a dip in the sheet, and if a small marble rolls nearby, it will follow a curved path around this depression. Of course, this image is imperfect, because it shows only 2 spatial dimensions. In reality, general relativity describes a 4-dimensional universe. 3 dimensions of space and 1 dimension of time. Together, these form what we call space-time. Thus, the Earth revolves around the Sun, not because it is pulled by a mysterious force in the Newtonian sense, but because it follows the curved geometry of spacetime distorted by the Sun's mass. Another essential consequence of this theory is that time is not absolute. By that, I mean that time does not pass at the same rate everywhere. The stronger the gravitational field, the more slowly time passes. This is what is called gravitational time dilation. In concrete terms, a clock placed near a massive object will run slightly slower than a clock located farther away. This effect is tiny in everyday life, but it is very real. It has been experimentally verified with atomic clocks placed at different altitudes. It even has to be taken into account in the operation of GPS satellites. Otherwise, the measurement will quickly become inaccurate. This idea is sometimes illustrated in popular culture. For example, in the movie Interstellar, where time does not pass in the same way depending on how close one is to the black hole. To continue, one of the pillars of general relativity is the equivalence principle. It states that locally, the effects of gravity are indistinguishable from the effects of acceleration. What does that mean? For example, imagine a person locked inside a windowless cabin, unable to see anything from the outside. If that cabin is sitting on Earth, the person feels that weight. But if that same cabin is in space, far from any star, and is accelerating upward, the person will feel a similar force. We see this in the recent movie Project Hail Mary, or even in the movie The Martian, where acceleration is used to simulate gravity. In both cabin scenarios, the local experience is practically the same. A person cannot tell whether they are in space or on Earth. This idea was decisive for Einstein because it allowed him to connect gravity with accelerated motion. Finally, general relativity also rests on the principle of general covariance. This means that the laws of physics must keep the same form regardless of the reference frame chosen, even if that frame is accelerating or described using complicated coordinates. In other words, the laws of the universe do not depend on the way we observe or write them. They must hold everywhere and for all observers. This is a very strong requirement, and it gives general relativity its universal character. That covers the principles. We now need to talk about something just as important, the consequences. Curvature of spacetime does not only bend the path of planets, it also bends light. This is what produces what we call gravitational lensing. Basically, when light coming from a distant star or galaxy passes near a very massive object, such as a galaxy or cluster of galaxies, its path is curved. The result can be spectacular. The distinct object may appear distorted, magnified, or even visible in multiple images. This phenomenon is now used in astrophysics to observe very distant objects and to detect the presence of invisible matter, such as dark matter. More importantly, general relativity also predicts the existence of extreme objects, black holes. When a very large mass is concentrated into a very small volume, the curvature of spacetimes becomes so strong that it prevents even light from escaping. Around a black hole, there is a boundary called the event horizon. Once this boundary is crossed, nothing can return to the outside. At the center, according to classical theory, matter will be compressed into a gravitational singularity. In this region where physical quantities becomes extreme and the curvature of spacetime becomes infinite, and where our current models are no longer sufficient. This also shows that general relativity, despite its power, is probably not the ultimate theory of gravity. Another major prediction of Einstein's concerns gravitational waves. These are ripples in spacetime produced by very violent events such as the merger of two black holes or two neutron stars. For a long time, these waves remained a purely theoretical prediction. Then they were detected for the first time in 2015, a century after they had been predicted. This discovery was a spectacular confirmation of general relativity. It also opened up a new way of observing the universe, no longer only through light, but also through the very vibrations of spacetime itself. To conclude, general relativity profoundly changed our view of the world. It replaced the idea of gravity as a simple force with a far richer vision, in which space and time form a dynamic structure that can be deformed. It made it possible to explain anomalies such as Mercury's perihelion, and to predict time dilation, gravitational lensing, black holes, and gravitational waves. More than a century after its publication, this theory remains one of the greatest successes in science. It shows us that the universe is not a fixed backdrop, but a living fabric curved by matter and energy, within which the entire history of the cosmos unfolds.